Hey guys, I'm not here today, so I'm going to go through the worksheet with you in this video, and then I'll leave you some time to try the homework. If you kind of get the gist of this video, it's not one of our more complicated topics. So we're back on vectors. This worksheet will be posted, filled in on Haiku if you want to print it out. Last couple of days we've looked at adding and subtracting vectors and multiplying vectors by scalars, but numbers. But you might be wondering if there's a way to multiply two vectors together. There's not a straightforward method of multiplying vectors as we think of multiplication, but there are a couple similar operations, one of which we will study. It's called the scalar product. You'll also see it sometimes called the dot product. And if you have two vectors, so let's say one vector is u1 and u2, and remember that means the vector that starts at the origin and whose tip lies at coordinates u1 and u2. And you have another vector v, which is v1, v2. So that's a vector v who, if you start its tail at the origin, its tip lies at coordinates v1, v2. We have a kind of simple way of multiplying them together called the dot product, which is given by this formula. Now what does that mean? That means you multiply the u1 and the v1, multiply the u2 and the v2, and add them together. So for example, if I had a vector u equals 1, 3, a vector v equals -2, 6, then u dot v, or u scalar product v, is okay, u1 v1 plus u2 v2, which would be equal to 1 times -2 plus 3 times 6, -2 plus 18, which is 16. So this, kind of strange way of multiplying vectors, the dot product, would give 16. And we're going to look at what this kind of means geometrically in a moment. But for now, let's just get used to this algebraic definition. So we can also ask the question, what would this look like if we wrote our vectors using standard unit vectors? Remember, standard unit vectors would be like this. u1 I plus u2j, that's what u would be. V would be v1i plus v2j. And remember, I and j are just vectors that point one direction, one unit, horizontally, that's I, and one unit vertically is j. And of course we can do u dot v here. You would get the same formula. So you multiply the two i's together, multiply the two j's together, and add them up. If we had a 3D vector, so u is u1, u2, u3, so now it needs 3 coordinates to place its tail, and v is v1, v2, v3, then u dot v, in very similar fashion, would be u1, v1 plus u2, v2 plus. So same thing, you just add in this third dimension. Okay, so here's an example. Let's calculate the scalar product u dot v if u is 3i plus 2j and v is -i minus 5j. And remember, this is the same as saying u is 3, 2, and that v is -1, -5. So u dot v is u1 v1 plus u2 v2, which is 3 times -1 plus 2 times -5, -3 minus 10, which is -13. Now here is why the scalar product is interesting. It tells us something geometric about our vectors. So let's say we have two vectors, u and v. And let's place them so that their tails are touching at a single point. And let's make a vector here. And this is the vector v minus u. Because u plus v minus u gives me v. Now there's a little fact that we need to talk about these vectors. And that is the fact that if you dot a vector with itself, so if u dot u, well, that would be u1 plus u2 u2, which is u1 squared plus u2 squared. And that is the length of the vector u squared. Because if you remember, thinking back, so we're thinking, the length of vector u, it's just a Pythagorean theorem, the length of a vector is this. Okay, so what does that have to do with anything? Well, let's look at the angle between vectors u and v. Okay, so using the cosine law, I know the length of the side opposite, so the length of v minus u squared is equal to, that's like the c squared in our cosine law, is u squared, that's like a, plus v squared, which is like b, minus 2ab cos theta. That is the cosine law on this triangle. But on the other hand, I know that v minus u squared, also we know that v minus u squared is equal to, well, from this property we looked at here, is also equal to v dot u, no brackets, sorry, just v dot u, actually v minus u dot v minus u, I'm sorry. And because we can distribute the dot product, we would get v dot v minus u dot v minus u dot v plus u dot u. If you dot something by itself, you get its length squared minus 2u dot v, this is a dot, plus the length of u squared. And now we can compare these two. So I'm going to give myself a bit more space. Insert, draw. So we can compare these two. These are both equal to u dot v. So we can say, okay, then length of u squared plus length of v squared minus 2 u v cos theta is equal to length of v squared minus 2u dot v plus the length of u squared. And now we can do some canceling, cancel, cancel. And even the negative 2's we can cancel. So that means that on the right we have u dot v, and over here we've got length of u times the length of v times the cos of theta, which is what we were actually trying to prove. So I can, if I know u and v, I can get their dot product and their lengths, and I can calculate the angle between two vectors. So let's do a practical example here. We want to find the angle between these two vectors, and let's see, well, u, meaning you go over 3 up 2. So say this is u, and v we go left 1, down 5. So let's see. Now let's draw v first. It doesn't really matter. It goes like this. This is v, and then u will be something like this. And we want to get the angle between them. So we know that u dot v is length u, length v cos theta. u dot v is 3 times -1 plus 2 times -5. The length of vector u is square root of 3 squared plus 2 squared times the square root of -1 squared plus -5 squared times the cos theta. So this is -3 minus 10 equals the square root of 14 times the square root of 26. Sorry, this should be 13. Cos theta, so cos theta is -13 over root 13 root 26, and which is -root 13 over root 26, which is -root of a half. Okay, so that is actually a special angle because that's -1 over root 2. So we know where is cosine positive, or negative rather. So it could be either of these angles with a reference angle of 45 degrees. We always take the angle less than 180 degrees. So in fact, theta here should be 135 degrees, which means I obviously drew my picture a little bit incorrectly. You would have an angle of 135 degrees between, which means it would look something like, you know, some steep curve here, and this would be 135 degrees. Okay, so that is why the dot product is useful for us. We can calculate the angle between vectors. Now your homework is page 274 in your workbook. It's actually this weird looking page. So at the back of your book, you have these vectors pages that look kind of weird. It's this page 234. Thank you guys.